Our planet Earth is a dynamic and ever-changing place. While we experience the beauty of its landscapes and the wonder of its oceans, there are forces at work beneath the surface, hidden from our everyday view. These forces, powerful and unpredictable, are responsible for one of nature's most awe-inspiring phenomena, earthquakes. Imagine the ground beneath your feet suddenly starting to shake. The earth seems to sway and roll, throwing you off balance. Buildings tremble and objects crash to the floor. This is the unsettling reality of an earthquake, a sudden and violent shaking of the ground that can have devastating consequences. Earthquakes are a stark reminder of the immense power that lies within our planet. They are a testament to the constant motion of the Earth's crust, a reminder that our world is far from static. Understanding what causes earthquakes and how they impact our lives is crucial, not only for scientific curiosity, but also for our safety and well-being. In the sections that follow, we will delve into the science behind earthquakes, exploring the forces that drive these seismic events. We will examine how earthquakes are measured, where they occur most frequently, and the profound impact they have on our built environment and human lives. To understand earthquakes, we must first journey deep beneath the Earth's surface. The Earth's outer layer, known as the lithosphere, is not a single solid shell, as one might imagine. Instead, it is broken into several massive pieces called tectonic plates, which fit together like a giant jigsaw puzzle. These plates are in constant motion, albeit extremely slow, driven by the heat emanating from the Earth's core. They drift atop a semi-molten layer called the asthenosphere. As these plates move and interact, they can collide, pull apart, or grind past one another. The majority of earthquakes occur along the boundaries of these tectonic plates. When the stress at these boundaries exceeds the strength of the rocks, they break, releasing a tremendous amount of energy in the form of seismic waves. These waves travel through the Earth, causing the ground to shake. This shaking is what we experience as an earthquake. While most earthquakes are linked to plate tectonics, volcanic activity can also trigger these seismic events. As molten rock, known as magma, rises within a volcano, it can fracture surrounding rocks, causing tremors. These volcanic earthquakes are typically smaller in magnitude than those associated with tectonic plate boundaries, but they can still pose significant hazards, especially in areas with active volcanoes. When an earthquake strikes, one of the first questions we ask is, how strong was it? To measure the magnitude or size of an earthquake, scientists use a logarithmic scale called the Richter scale. Developed in 1935 by Charles Richter, this scale provides a numerical value that represents the amount of energy released by an earthquake. The Richter scale is logarithmic, meaning that each whole number increase on the scale represents a 10-fold increase in the amplitude of seismic waves and a 32-fold increase in energy released. For example, a magnitude 6.0 earthquake releases about 32 times more energy than a magnitude 5.0 earthquake. Earthquakes with magnitude below 2.5 are generally not felt by people but are recorded by seismographs. Earthquakes with magnitudes of 7.0 or greater can cause widespread damage, while those with magnitudes exceeding 8.0 are considered major earthquakes capable of causing catastrophic destruction. The Richter scale has limitations, especially for very large earthquakes. Today, seismologists often use other magnitude scales, such as the moment magnitude scale, which provide a more accurate measure of the energy released by large earthquakes. However, the Richter scale remains a widely recognized and commonly used measure of earthquake magnitude. While earthquakes can occur in various parts of the world, they are not evenly distributed across the globe. The vast majority of earthquakes, including some of the most powerful ever recorded, occur along narrow zones known as seismic belts. These belts coincide with the boundaries of Earth's tectonic plates. One of the most seismically active regions on Earth is the Circum-Pacific Belt, also known as the Ring of Fire. This horseshoe-shaped zone encircles the Pacific Ocean and is responsible for approximately 90% of the world's earthquakes. The Ring of Fire is characterized by intense volcanic activity and frequent earthquakes, a testament to the dynamic interplay of tectonic plates in this region. Another significant seismic belt is the Alpide Belt, which stretches from the Mediterranean region eastward through the Himalayas to Southeast Asia. This belt is associated with the collision of the Eurasian plate with the African, Arabian, and Indian plates. Understanding the geographical distribution of earthquakes is crucial for assessing risks and implementing appropriate building codes and safety measures. By studying historical earthquake patterns and monitoring seismic activity, scientists can identify areas prone to earthquakes, allowing communities to prepare for these potentially devastating events. The destructive power of an earthquake extends far beyond the initial tremors. Earthquakes can trigger a cascade of secondary effects, each capable of causing significant damage and posing threats to human life. One of the most common and hazardous secondary effects is ground shaking. Ground shaking is the most immediate and direct effect of an earthquake. The intensity of ground shaking depends on several factors, including the magnitude of the earthquake, the distance from the epicenter, and the local geological conditions. Soft soils, for example, can amplify ground shaking, leading to more severe damage in areas with such soil types. Earthquakes can also cause the ground to rupture, creating fissures and cracks in the Earth's surface. These ruptures can be extremely dangerous, damaging buildings, roads, and pipelines. In some cases, earthquakes can trigger landslides, especially in mountainous areas or regions with steep slopes. The shaking weakens the stability of slopes, causing rocks, soil, and debris to slide downhill, potentially burying homes and blocking roads. In coastal areas, earthquakes can displace large volumes of water, generating tsunamis. These giant waves can travel across entire oceans at high speeds, reaching heights of over 100 feet when they approach the shore. Tsunamis can inundate coastal communities, causing widespread destruction and loss of life. As we move forward, scientists are tirelessly working to unlock the mysteries of earthquake prediction. The goal is to better understand seismic activity and to develop technologies that can forecast these natural events with greater accuracy. One of the most promising areas of research is the study of seismic precursors, small-scale disturbances that sometimes precede a larger quake. By monitoring these subtle changes in the Earth's crust, scientists hope to identify patterns that could signal an impending earthquake. Another cutting-edge approach involves using artificial intelligence and machine learning algorithms. These advanced systems can analyze vast amounts of seismic data, identifying trends and anomalies that human researchers might miss. With AI's ability to process information at incredible speeds, we inch closer to the possibility of real-time earthquake warnings. Additionally, global networks of seismic sensors are being expanded and refined. These sensors can detect even the slightest ground movements, providing crucial data for researchers. Enhanced communication technologies also allow for faster dissemination of warning alerts, giving communities precious extra seconds to prepare and seek safety. While the dream of precise earthquake prediction remains a challenging frontier, each scientific breakthrough brings us one step closer. Through continued innovation and global collaboration, we strive to reduce the devastating impact of earthquakes and protect lives around the world.